Okay, so we're going to take a look at some revolution of solids problems, and not terribly difficult, but these are tend to be a little bit challenging. It's one of those topics of calculus that always is difficult for people because of the visualization that's involved. Sometimes it's just hard to understand what those shapes are that are being implied by the question. So anyway, let's get going on this. So I went ahead and I drew some of the pictures in advance to make that process a little bit faster. But so what we have is this shape. So keep in mind, we probably generally know what y equals 1/4 x squared is. Y equals 1/4 x squared is just a nice simple parabola opening up. So of course, this is the same story, just opening to the side. So if this parabola opens to the side, because it's really the inverse of it. It's swapping those x's and y's. So it's going to open to the side. Y equals x is pretty simple. But we want to figure out what happens if we try to revolve this around the x-axis. So clearly what we're going to end up with is some new piece coming down here with this. And then we're going to interior-wise have these nice little circles inside, all right? That are being removed from the story, but then from the outside, this is the part that is left, which is why this is actually known as the washer method, okay? So if that's the story, when we look at it, what we're gonna have is some kind of a pi r1 squared minus some kind of a pi r2 squared. And that's going to be the case for all of these particular problems. When you try to revolve simultaneously two curves and deal with that area in the middle of them being that region of revolution, that's just what happens every single time. So we could actually start by writing that on all four of these problems that we have, A, B, C, and D. Now, our biggest job is to figure out what R1 is and what R2 is. So as I look at it, as I look to this outer curve, this radius is really the y value for the curve. So I'm going to call this pi y1 squared minus pi r2 pi y2 squared, because the inside radius is also a version of y. See, from here to here, notice it's going up and down in the y direction, so some version of y. And then the thickness, if you were to look at it in this way, we've got these kind of discs coming out like this, which we actually call a washer. The thickness of them is running in that x direction, so that's going to be a dx. So let's see what we've got. I'm looking up here, the curve, this says, hey, let's take y squared. Well, so what I notice is that y squared right here is, in fact, 4x perfectly. So I don't even need to do any work on that one. And then now also notice that I saw that pi was a shared constant, so I factored it in front. And let's go ahead and look at y2 squared. But of course, y2 is just x. So if I square it, I get x squared dx. And that's turned into a pretty simple little thing. Now, I haven't put my bounds on. I'll take care of that in a moment. But if we took our integral, we would get 2x squared minus 1/3 x cubed. Now, we don't need a plus c because this is going to be a defined interval. So let's figure out, where do these things cross? So if we were to look at where these two things cross, I would want to know if y and x are in fact the same thing. Then over here, I could replace this with x squared equals 4x. Now, remember we said don't divide both sides by a variable. In fact, move it across. Set it equal to 0, so that allows you to factor. And I think quite quickly you're going to be able to see that those two x values are going to be 0 and 4, which, because y is x, that means both x and y are both 0, 0, and 4, 4. I'm going to put this over here since this particular picture is a little cleaner right now. But that's going to be my bounds of integration. That's everybody's favorite thing because we don't have to work quite so hard on it. Excuse me. And so when I did that particular story, I got 32 pi over 3. Now, moving to our secondary question, we're going to have the same idea, the same region, but we're going to revolve it over the other axis. So we are going to have some kind of a line that's coming out here. So we have an exterior kind of a cone shape, but then inside we have these kind of little pieces. So it is a cone where somebody has hollowed out sort of this belled region that is there. So we have the same idea, but the first radius is going to be some version of x. So we're going to do pi r1 squared minus pi r2 squared, but it's some kind of an x that is being squared and some kind of an x that is being squared. So the outer x is the line, but I already know that x is in fact y. So I'm going to go pi y squared. And over here, if I wanted to get x squared by itself, now right here, you notice that a little bit ago, I went ahead and took the time to isolate x, not that it was very difficult. But if I squared that, I get 1/16 y to the fourth. And this is going to be a dy because if you look at it this way, as you slide each of these pieces up, their thickness is sitting in the y direction. So there's my washer in that case. And again, just like x, y is going to go from 0 to 4. Now, again, the integration on this particular story is a fairly simple one. We're going to get 1/3 y cubed. We're going to get y to the fifth, which I need to then divide by 5, which is kind of a large number at 80. Don't usually get denominators quite that big. And so I ended up with, after I analyzed this, I got 128 pi over 15. Again, each of these is going to be in cubic units. We don't know if that was in inches or feet or whatever, it doesn't matter. But moving on to the two harder problems, and these are harder for a couple of reasons. One of them is the picture is a little tougher, but secondarily, the actual algebra that actually undergirds that calculus is a little tougher. So when we take this vertical line out here at x equals 4, and we try to revolve it this way, this is actually going to mimic much like this problem right here. Since it is a vertical line of rotation, it's going to be a dy story. So that's kind of an important little piece. So again, going back to the well, we're going to have some kind of a pi r1 squared minus pi r2 squared. And here's where it gets a little tough. Keep in mind the separation from here to here, that is a version of x1. This is some version of x2. Now, the reason I call this x1 is because when I look from this vertical line right here, x1 is further away than x2 is. So I'm calling x1 the far curve and x2 the near curve. But if the distance all the way across is 4 and the distance here is x1, then the real radius r1 would actually be 4, take away that x1. And similarly, if this is x2, then this other radius right here, r2, would be 4 minus x2. Now, that little binomial is really what is going to make this problem a little bit stickier when it comes to trying to analyze. So I'm going to replace r1 with 4 minus x1 squared, and I'm going to replace r2 with 4 minus x2, again, squared dy. So I would like to see you just very methodically just go one line at a time. Don't try to do it all at once. It's just much easier if you take a moment to think logically and clearly what's going on. I know that x1 is, in fact, the curve. So I need to figure out what x1 is. Well, earlier I already wrote down that x1, the curve part, was 1/4 y squared. So let's do that. So I've got 4 minus 1/4 y squared, again, squared, because all I did is replace x1 with its equivalency in y. And before we said the inside curve was y equals x, so I could take x out and put y in its place. And we're kind of ready to go. But unfortunately, this is the tough part because in order to analyze this, I do need to multiply this thing out. I cannot do this as it sits right now. I need to do some basic algebra. So one of the things that I have noticed that people sometimes struggle with, sorry, I'm off screen for just a second, people seem to struggle with is that when, let me pause this for one moment. Hello? Okay. I don't know either. Yeah, let me come down in a couple of minutes and I'll help you. I'm kind of making a video for my calc kids. Okay. All right. Thank you. Bye. All right. Sorry. I hope that actually was not recorded. But anyway, so if we're taking a minus b and we square that, because really in both cases we have a binomial that is being squared. So remember when you take a minus b times a minus b, you get the first is a squared. I get an AB here, but an AB there as well, but they're both negative. So that's looking this way. And a B squared comes at the end. Now, by knowing that, we can actually, without working quite so hard, think about this is going to be 16, right? Because 4 squared is 16. This puts A and B together, that's 4y, so it'd be 8y. And then we square the last piece. Now, this one was fairly simple to do, but this one over here is a little tougher. So 4 squared, of course, is 16. Right here, if I put these two together like this says to do, AB, 4 times 1/4 would actually be negative 1y squared. But then I have to double that, so it'd be negative 2y squared. And lastly, I need to square this remaining term, which is 1/16 of y to the 4th. Now, once we have that part taken care of course, with a dy, the math isn't really too bad because you see a few things like the 16s cancel quite nicely. We've got a negative 2y squared and we've got another negative y squared. So it looks to me like we have a negative 3y squared, right? We've got a 1/16 y to the 4th, and we've got a double negative on this with an 8y, and putting it all together, we get a not terribly unpleasant 64 pi over 5 after we plug in those numbers. Now notice I didn't do the antiderivative because I'm assuming at this moment we can do the power rule. It's very similar to some of the previous questions answered. So I'm not going to take the time to do that, but I do want you to do that. I could, but I don't want the video to be too long. Okay, now the last one. The last one is a little bit interesting because unlike this one where the curve is to the right, then that effectively reduces the radius. It's because it's moving towards it. This one, I pull the center of revolution away, and that actually changes the story. So it took me 2 units just to get up to the original axis, and then I had to go from there up a little bit more to that first y value. So in my pi r1 squared, that's really 2 plus y1 that is being squared. And then for my pi r2 squared, similarly, it's 2 plus some other y value that is being squared. Let's make that 2 plus y2 quantity squared. And again, because it's revolving in this direction, it's similar to question A in that all of the washers are oriented in the x direction. So these are going to be a dx. Okay, so now we're ready to go. So we got a pi. I'm going to go 2 plus y, but again, y, as we established earlier, was the square root of 4x. Again, right here, if y squared is 4x, then y itself is the square root of that. And keep in mind, the far one is the curve. The near one is the line, and y is x, so we're just going to go ahead and make an easy switch. Again, not trying to make a big deal about it, but playing the same game that we did with this part right here with that binomial expansion. before we ever deal with the integral, 2 squared is 4. If you take 2 times the root of 4x, you get 2 roots of 4x, but we have to then make that 4 roots of 4x. And then plus this one squared, because that's b squared, that's plus an additional 4x. And then over here, we're going to subtract 4 plus 4x plus x squared. Now, there is a slight difference in that there is a plus on this question, which means these are both positive, and therefore so is this. So mathematically, it's almost the same thing as the previous one, a very small nuance differently. Now, there are a couple little things like before we go any further, the square root of 4, of course, is 2. So you could replace this part with 8 roots of x or 8x to the half. Similar to the previous question, you could do some little things like canceling out those 4s. We have a 4x here and a negative 4x here. Those things cancel out as well. There's a lot of nice little things that actually occur within this problem, but play with it and make sure that that actually works for you. But I ended up with 64 pi over 3. Okay, now let's take a look at our last two that I was hoping to accomplish within this one. Back to, in a sense, what should be an easier problem, just area between curves. But what makes this one a little bit different is that y squared equals 3 minus x is not a function. And that's going to create a problem. And I'll try to show you what I mean by that here. But what I like to do is, because I'm not that good at dealing with those problems that are not functions, because I don't have them memorized. But instead of thinking about y squared equals 3 minus x, if we really thought about x equals 3 minus y squared, or in fact, if you put it in a different way and thought of this as y equals 3 minus x squared. So if we had y equals 3 minus x squared, we would know that it has a vertex at 3 and it's a curve that is extending down. Well, in the same way, that's what's going to happen if you have x equals 3 minus y squared. We're just swapping our x's and y's. It's going to have its vertex at 3 on the x-axis and extending to the left, because it's really just a mirror image of the one that we had. So that's going to create us a little bit of a problem if we're dealing with this, because when I do my typical Riemann sum, I can't make a bar that goes this way, because the height would be going from the curve to itself. That works great in this situation, but it doesn't work well in this situation. What we need to do instead is consider the curve going this way, because now it is well defined. So we're going to be forced to do a dy. And the other piece of this story is we have y squared equals negative 4x, or x equals negative 1/4 y squared. So it's kind of this curve right here. Similar logic to the previous one. Now, if you set those things equal, in other words, take, I guess the easiest way to me would be to say, since they're both equal, we got a y squared in both cases, we could set those equal. And what you're going to find out is that x is negative 1 when you do that. So again, what I did is I isolated y squared in both stories so that then I could set those pieces equal to each other. So notice right here, you could say that y squared is 3 minus x, and y squared is negative 4x. I wasn't going to do this, but there we go. Divide both sides, you get negative 1. That's that place where those two cross. And if we plug that back in, if x is negative 1, negative 4 times negative 1 is 4. So if y squared is 4, we either get 2 or possibly negative 2. So as I set this thing up, what I had to do, because it is now going to be a dy, I needed to find this region right here, which is the top minus the bottom. So it is this top curve, which is this guy, the 3 minus y squared curve, minus the other, because this is in the x direction. So what I did is I did the outside one, 3 minus y squared, minus the inside, which is negative 1/4 y squared, dy, and y is going from negative 2 to positive 2. But of course, we've done this a lot. Instead of going -2 to +2 based on the symmetry, let's just go ahead and double that. Now, it turns out this one is not so bad because we don't have to square it. We're not doing a volume of revolution, so that's not a big deal. The integral of 3 is 3y. It looks like I've got a 1/3 y cubed here. Now, I could have combined these like terms. I just chose not to. And I get a y to the third, and I have to divide by 3, so I've got a 1/12, double negative, life looks good, and we're looking at 0 to 2. And turns out this time we get a really super nice 8. Awesome. Okay. And last but not least, one where we actually do not get away with using symmetry. What a bummer. But again, we've got two curves, and if you thought of y equals 1/2 x squared minus 3, that would be easier to picture. Y equals 1/2 x squared minus 3 would be a nice little parabola with a vertex at -3. So we're just going to flip it this way, and it's going to have this be the x-axis and this be the y-axis to make that work. So here we go. So we've got a curve going this way, and y equals x plus 1 is a little line going this way. So we're looking for this region right here. And honestly, the easiest way to look at that is going in this direction, because it is clear who's on top and who's on bottom. So notice the line is now the one to the far right, and the curve is the one to the left. And we do have to do a little bit of work to solve where those things are equal to each other. Well, as it turns out, if we did that, I could say that 1/2 y squared minus 3 is x. And over here, y minus 1 is also x. I decided to multiply by 2, move things around just a little bit. Hopefully I did that exactly right. I'm just double checking, and I did. I thought it was easier to solve this problem by completing the square. So what I did is I added 1 to both sides. I got y minus 1 squared is 5, which makes y, I'd have to take the square root of both sides and then kick the 1 across. Well, that's really kind of an annoying looking value. So I know that my y values, and that's okay because it is a dy, are going to go from 1 minus root 5 to 1 plus root 5. And this is going to be a dy. And of course, the curve that is sitting inside, the outside curve is, again, going to be y minus 1. The other curve is going to be 1/2 y squared minus 3. Now, the only other thing that I would say in doing that is that if that's how we're going to have to play this game, probably the easiest thing to do would be to use our calculator, because I don't think we're going to be able to integrate that and plug in such a terrible looking number. So let's go ahead and see what we've got. So I'm going to clear this out and use x minus 1, because my calculator doesn't understand the difference, minus 1/2 x squared plus 3. And I could have combined some terms, but it doesn't really matter. I'm going to take 1 minus root 5, and I'm going to store that as alpha a, and I'm 1 plus square root of 5, and I'm going to store that as alpha b. And now I'm going to do my math 9. I'm going to do that f and int from a to b of, let's see, alpha trace y1 dx, and that's what I ended up getting. I got 7.45355. And something feels a little awkward to me about that, because my notes actually claim that it's actually 0.7454. And that's what I got previously, but I don't see anything wrong with my mathematics. I definitely have a y minus 1. I have a -1/2 y squared, a double negative on that. I went from y minus root 5 to y plus root 5. I believe this is the correct answer. I think my notes may have been wrong. So anyway, that should do it for this episode. There you go. I hope that was helpful. I'll see you back in class.